Ben is a PhD student at Queen's University, not too far from where I am. And he's going to speak to us about behavioral models of visual working memory. Your turn, Ben.
You can see my screen and hear me?
Yep, all's good.
Perfect. So yep, my name is Ben Cuthbert. I work at Queen's University with Doctors Perret and Blom. And today I'm going to talk to you about a visual working memory paradigm called the whole report paradigm. It's relatively new on the working memory scene, and I'm going to talk about some analysis that we've done of the data there and how some of these data sort of suggest that common models of visual working memory do not capture aspects or don't capture behavior on this task. So first, I'm just going to talk to you about what I'm calling a typical delayed estimation task, or like a single report delayed estimation task. Basically, this task starts by presenting a subject with some stimuli. Then there's a brief delay period. Following that, one of the locations of the stimuli is probed. Okay, so like this is the probe here. And then the participant or subject is required to report the stimulus the stimulus value that they remembered at that location. So in this case, they have to remember the color and report that they saw the green at that location. But really the important thing here is that the stimuli used, and they can be color, orientation, or even faces, things like that. The important thing is that this stimulus dimension is continuous, because when you have a continuous stimulus dimension, every time there's a report, you actually get an angular, in this case, an angular measurement of the error. So here you get an angle telling you how far off the correct color they were. And when you look at these distributions, on the right here, this is an example of a bunch of different distributions, error distributions that you get at different set sizes. So this is when one item is presented versus 2 versus 4 or 6. And these distributions are really nice because they're very amenable to statistical analyses. And a lot of people spend a lot of time analyzing these sort of aggregate error distributions with the assumption that the sort of shape and precision of a distribution like this tells you something about the representation that someone had stored. Okay. In comparison, the whole report task, which was introduced by Kirsten Adam and colleagues in 2017, in the whole report task, rather than just having one probe and one report per trial, which is really common, they required their participants to actually report the stimulus of every single item that they presented within a trial. And in their case, they had a bunch of different conditions. So sometimes the probe order was randomized. Sometimes the participant was allowed to choose. I'm going to focus on the condition where the participant was allowed to choose. And one of the reasons that we're interested in this task is that they made their code and data publicly available, which is really great. And some people have already taken these data and they've started fitting models developed originally in the single report context. And they've been fitting these models to the new data, using them to draw some conclusions. The task is also increasing in popularity, and a bunch of other people have started to use it. Okay, so just quickly give you a little look at what the report, or sorry, I should say the error distributions look like in a task like this. On the right, I have the sort of classical single report distributions. And we see that in the aggregate, so when you collapse across all participants, collapse across all responses within a trial, in the aggregate, the distributions look pretty similar. We see that when only one item is presented, you have quite accurate reports. These are all, again, angular errors. And then as you present more and more items, the errors become a little bit more diffuse and people seem to be a little bit worse at remembering. So really similar pattern to what you see in the single report context. What's nice about the whole report is that you can actually subdivide these errors. So here I'm showing everything here these are the same data that I've showed here. So this is at set size 6, but now I'm showing you the error distributions separated by the order in which they were reported within the trial. Okay, so light green to dark blue is the order throughout the trial. And we see a kind of a similar pattern where people are quite precise in the early responses. And then later on, it's unclear whether, are they guessing or do they have just a little bit of information about the items. So Kirsten Adams originally spent most of their time focusing on these distributions and seeing what conclusions they could draw there. But what they did not look at are the actual joint distributions. So how are the reports made within one trial? So when you're reporting items that were simultaneously presented, how are these distributed relative to each other? So what I'm going to show you here are the joint distributions between the first report made in a trial. So the y-axis value, these are not errors, these are the actual stimulus values reported first on the y-axis. And then each subsequent plot is the joint distribution between the first report and the second report, or the third, fourth, fifth, sixth, etc. Okay, so what we see here is that the first report and the second report within the same trial actually have a really strong circular correlation. And I'm going to talk about these correlations a bit. They're circular correlations, so they look a little bit different than linear correlations. If anyone has questions about that, ask me. But really what I want to focus on is that there's this strong circular correlation between the first and second reports within the same trial. And we lose that a little bit when you look at the third report. But then as you get later in the trial, there's actually sort of a different dependency going on where people seem to be biasing their later trial responses away from the early responses that they made. Another way of looking at this is to look at the relative distance between reports made on the same trial. Okay, so this is a histogram of the differences between the first report on a trial and the second report. Okay, so this is just a different way of looking at these data. We see again, there's a huge peak in the middle here. So people are really choosing almost the same color or a very similar color in their second report as their first. And as you go later into the trial, they actually seem to be biasing their reports away from the early reports. The reason that I'm focusing on this, and that I think that this is a kind of a key finding, is that a lot of models of working memory, and specifically models developed to explain sort of these error distributions at the single report generated by our single report tasks, these all tend to assume that stimuli are encoded independently, that you're shown this array of stimuli and that each one gets its own little representation in visual working memory. But this shows that there seems to be something else going on. The relationship between items or stimuli that people are reporting is completely unaccounted for in these models. So there are some models that explicitly discuss or that explicitly address the relationship between stimuli. And actually, Fosca's talk sort of had a similar idea to this, where things are encoded together or in a sequence. I'm calling this hierarchical or ensemble coding, but there are many, many different names for these and many different models that people have used. One that we could call like a naive ensemble coding is the idea that when presented with an array of stimuli, people are sort of implicitly extracting the mean value of the array. Okay, so this is discussed at length by Naud, Oliva, a bunch of others have talked about these sort of things. And just to illustrate, on the x-axis here, I'm showing again stimulus value. This time I've actually color-coded the bars. So these bars would all be stimuli presented on the same trial. And if you're asked to report this dark blue color, in this case, if there was a bias toward the ensemble mean, if people were using that ensemble mean to help them compress memory or something like that, we'd expect a bias toward this ensemble mean. An alternative was introduced in 2018 by Nasser et al. And they did a whole bunch of different modeling, and they essentially predicted that a report should be biased toward the nearest neighbor, so that there should be this bias between reporting an item and the closest item that was simultaneously presented. Yet another very similar variation to this kind of bias is called hierarchical Bayesian clustering. So it was originally introduced by Brady and Alvarez in 2011. Orhan and Jacobs sort of came up with a more general case. And effectively, they assume that people are extracting clusters from an array. So in this case, you could imagine that these three similar red colors would be grouped together. These three bluish colors would be grouped together. Here, the histogram is a posterior over the cluster mean. I don't have time to go into the details of how I got this posterior, but feel free to ask me later. And this predicts a bias toward the cluster mean. Okay. In a lot of these cases, these biases, the direction of the bias can be the same, but the actual magnitude of the biases predicted are different. Regardless of any of the differences, no matter how you slice it, I've done tons and tons of different tests. There are no significant biases toward any of these ensemble means or cluster means. So that I really haven't been able to find evidence for any of these biases predicted by hierarchical models in this data set. And then finally, just to make things a little bit more complicated, Chris and Adam et al. Didn't just use color for stimuli, they also used orientation. So they replicated every single condition with color and orientation. So here again, I'm showing you the aggregate error distributions for color. And then below that, the aggregate error distributions for orientation. And a lot of different people have used both of these stimulus modalities more or less interchangeably. And the common assumption seems to be that these are more or less encoded into working memory in a similar way. And at the aggregate level, that seems to be true. But then when you go and you look at the joint distributions or the relationship within the trial, and these are the same exact tasks, the only difference is that one uses color and one uses orientation, you see that participants seem to be approaching this task in a completely different way. None of the dependencies that we saw with color are present in the orientation condition, despite having the aggregate distributions look really similar. And I think this is interesting because, like I said, everyone assumes that these are the same, and people will even feed the error distributions into the same sort of models to make conclusions. But we're ignoring the fact that these seem to be completely different behavior. Okay, so in summary, within trial reports are not independent. So when stimuli are presented at the same time, people seem to have some sort of dependency between them. The fact that they're presented at the same time seems to have a huge difference in how they are reported. That's important because many models developed in the single report context assume that they're encoded independently. I was not able to find any evidence for ensemble or hierarchical encoding, which is sort of the main alternative model where stimuli are sort of grouped or chunked together based on some sort of compression optimization. And finally, different behavior when reporting orientation versus color. I threw in a few limitations here, just preempting what people might say. These are still aggregate data. We still get, this task gets you an error estimate for every single item on a trial, but we still have to aggregate them all together to get these sort of estimates of precision. And then finally, we don't have spatial position information. You can imagine that if people were using ensembles or clustering things together in visual working memory, that the spatial location on the screen would be very important. And there have been a little bit of modeling to sort of try to capture these effects. Unfortunately, we don't have access to the spatial location. All right, that's it. Thank you.
Thank you, Ben. That was great. Yeah, very interesting. I'm opening the floor for questions. We have 3 minutes. I have here a comment and a question that you can see. So Ivan Tomic first congratulates you on the talk and then says, you're talking about encoding correlations, but aren't these reporting correlations? So distinguishing encoding and reporting correlation. Saying
you don't see such strong correlations toward other presented colors, but you do towards responses. So you're absolutely right. When I say encoding, I'm just adopting the language used by people who model these tasks in the past. These are absolutely just the reports that people are providing. I'm not really sure about the distinction that you're making though, because like we don't have access to any kind of encoded representation. Like all we have are these distributions of errors. So I'm not sure what you mean by, I guess I don't understand how you could have encoding correlations without reporting correlations. I'm not sure if you want to clarify.
Yeah, Ivan, you're welcome to clarify on the chat. If there's any other questions, you kind of answered my question. I was wondering to what extent like these history effects could be accounted for by some type of reinforcement learning model or some type of sampling theory. But the fact that you don't see these effects the same whether you have orientation or color would seem to go towards more like an encoding property, as you're saying.
Yeah, there is one paper that I could point you to if you're curious about that, by Matt Penicello et al. It's like 2019 Nature Communications paper. They basically show the aggregate, or not even aggregate, they show just the distribution of all reported colors across a task like this. And they show that the distribution is actually really peaked in certain colors, like people tend to report similar colors more often. And they present sort of a dynamical, they have like a drift diffusion model. And they they suggest that maybe there could be like attractors in memory centered on colors that participants have seen more often, either throughout their life or throughout like a block of trials. And they do quite a bit of modeling and analyses suggesting that maybe people are sort of biased toward commonly presented colors. So that's kind of like a reinforcement learning effect. But like you said, looking at the orientation distributions, they only did color, and looking at the orientation distributions, it makes it seem kind of, I don't know. It's hard to imagine how that would work.
Okay, thank you. That's a good answer. We have a last question. Chuan Wan here is saying, first, awesome talk. You presented 3 theories to adjudicate among, right? So other than ensemble and hierarchical, did you find evidence for the center surround account?
Yeah, it's kind of a bit disingenuous how I presented them, as if like these were the 3 competing theories. These are just 3 easy biases that I could explain quickly. I did not, if you're talking about center surround, I'm specifically referring to predictions made in this 2018 paper by Nasser and Michael Frank. I did not find any evidence. They reported a bunch of biases that they identified in their data in a single report task, and I could not replicate any of the biases that they reported. The center surround was just kind of part of the modeling that they suggested to explain those biases. Great.
All right. Well, thank you, Ben. I'd like to thank you for your talk, and thanking all the panelists again. Thank you so much. We'll be closing the session, and I hope you enjoy the rest of the conference.